Hello everyone, I'm Hongji from HKUST Guangzhou. Today, I'm presenting NoctuaXR, a real-time system that enhances video see-through perception in XR headsets under low-light conditions. The name comes from Noctua, the barn owl genus known for exceptional night vision. Picture this. You're in a dimly lit bedroom, wearing your XR headset and watching a show. You reach into a basket beside you for a snack. You look toward the basket, and all you see through the pass-through is a dark, blurry mess of noise. You can barely make out the shape of a bag. You pick one up at random, and you can't even tell what color it is. So you take off the headset. Just like that, you're out of the experience. This is the core problem. Video see-through lets XR headsets blend virtual content with the real world through a live camera feed. It's widely used in medicine, industry, education, and gaming. But in low-light environments, that camera feed falls apart. Colors wash out, noise takes over, and users experience eye fatigue. Consumer XR headsets today try to compensate with imprecise, image-based estimation, and it simply isn't good enough. There's no lightweight, affordable solution for consumer headsets. NoctuaXR changes that, using a $2 ambient light sensor and a real-time GPU shader running on the existing hardware. That's the gap we're filling. As you can see in this table, prior work falls into two camps. Algorithm-based methods, from histogram equalization to state-of-the-art deep learning, deliver impressive results, but they need significant compute. Even the most recent lightweight deep learning models can barely run in real time on desktop GPUs, let alone on the resource-constrained mobile chips inside consumer XR headsets. Hardware-based solutions, SPAD sensors, FPGA accelerators, are powerful, but expensive and complex. So the gap is clear. NoctuaXR is the first approach that is low cost, runs in real time on mobile XR hardware, and has been validated specifically for VST. Our work is built around three questions. First, can a sensor-driven enhancement meaningfully improve VST color accuracy and perceived visual quality in low light? Second, how does it compare to the $10,000 Varjo XR-4? And third, does better visual quality actually translate to better real-world task performance and less mental effort for the user? Our experiments are built to give empirical answers to all three. Let me walk through the pipeline. A digital light sensor continuously reads the ambient illuminance. That reading is sent to the headset 10 times a second through an Arduino, far faster than lighting conditions ever change in a typical room. Inside the headset, two predictive models calculate the right brightness and saturation adjustments. Those values go into a GPU fragment shader, which corrects every VST frame at the pixel level. Importantly, this runs as a post-processing layer on the Meta Pass-Through API. No camera firmware changes needed. And on the rendering side, the shader adds just 3.11% overhead on average. The hardware is intentionally minimal. The ambient light sensor costs about $2. It connects to an Arduino board, which reads the illuminance and sends it to the headset. The whole assembly mounts on the Quest 3 and adds less than 40 grams, lighter than a standard pen. Total hardware cost around $50, including the microcontroller. The philosophy here is simple. Good low-light enhancement shouldn't require expensive, specialized equipment. At the heart of the system are two calibrated models. For brightness, we use a 4-parameter logistic function, because the perceptual benefit of boosting brightness saturates. Beyond a certain point, more boost stops helping and actually hurts. The logistic model captures this naturally. For saturation, a linear model is enough. Both were calibrated across a range of light levels using a color checker card as ground truth. The GPU shader then applies these values to every pixel. Brightness is handled by uniform RGB scaling. Saturation uses luminance-weighted interpolation between the grayscale and the original image. We also have highlight protection to prevent overexposure in brighter regions, and shadow recovery, a gamma-like curve that pulls back texture detail in underexposed areas. The whole shader runs in real time at just 3.11% overhead. Our evaluation has three parts. First, an objective color accuracy study. We measured a color checker chart under standard illuminance across 20 light levels. Second, a perceptual quality study. 18 participants rated the VST view on a 5-point scale. And third, a daily task performance study. 16 participants in a 1-lux room, essentially moonlight level darkness, completed 4 realistic tasks. All 3 studies compared NoctuaXR against the MetaQuest 3 baseline and the Varjo XR-4 as a professional reference. The color accuracy results are striking. Looking at figure 7a, NoctuaXR clearly outperforms both systems below 40 lux. Here's the headline number. At 10 lux, roughly a candlelit room, NoctuaXR achieves a delta E of 10.9 compared to 34.7 for the baseline. That's a 69% improvement over the Quest 3, and it actually outperforms the $10,000 Varjo XR-4 at this light level. NoctuaXR holds this advantage across all illuminance levels below 40 lux. Above that, the baseline is already well optimized, and that's a trade-off we're comfortable with. The perceptual results tell an interesting story. At 5 lux, NoctuaXR scored significantly higher than the baseline, mean opinion scores of 3.00 versus 2.28, with a p-value of 0.035. And the scores for NoctuaXR and the Varjo XR-4 at 5 lux are essentially the same. Statistically, there's no meaningful difference. NoctuaXR also stayed consistent across all conditions, while the baseline dropped off sharply. So why didn't participants perceive the large objective color gap? Because at 5 lux, you're in the mesopic range. The human visual system shifts out of color vision mode. Chromatic contrast sensitivity drops, and people simply can't tell the difference between 2 color-accurate images at this light level. Once you can see well enough, perceived quality stops improving. All in all, NoctuaXR delivers perceptually equivalent quality to a device that costs 15 to 20 times more. The daily task study is perhaps the most compelling. In a 1-lux room, participants used each of the 3 setups to complete 4 tasks: finding keys, locating snacks, identifying medicine, and pouring water. The data shows a significant effect of setup on task completion time. Follow-up analysis confirmed that both NoctuaXR and the Varjo XR-4 led to significantly faster completions than the baseline. And critically, the difference between NoctuaXR and Varjo XR-4 was not statistically significant. NoctuaXR also significantly reduced subjective workload compared to the baseline. This matters beyond just usability. Doing everyday tasks in near total darkness without visual help is a real safety concern, and NoctuaXR addresses it at consumer device cost. NoctuaXR isn't just useful in the lab. On a night flight in a dimmed cabin, you can interact with your tray table without taking off the headset. In a dark car at night, a passenger can find something in the seat pocket without the dome light, which would create dangerous reflections on the windshield. In a shared bedroom, one person can use XR without waking the other with a bedside lamp. So let me bring everything together. NoctuaXR delivers a 68.59% color accuracy improvement at 10 lux. Perceptual quality matches the Varjo XR-4 even in very dim conditions. Task performance and workload are on par with a professional device. And all of this comes at just 3.11% rendering overhead, running on the headset's existing GPU with nothing extra beyond the $50 sensor assembly. We also want to be upfront about the limitations. We've only validated NoctuaXR on the Meta Quest 3 so far. Extending to other headsets is future work. The global brightness boost doesn't handle HDR scenes well. Local adaptive tone mapping is on the roadmap. In extreme darkness, sensor noise amplification is still a concern. A lightweight denoising shader could help. Head and hand tracking still degrade in low light, and that's a hardware constraint we can't solve with software alone. And because NoctuaXR adds visible external hardware, participants could tell which condition they were in. Future work should use a compact, form-matched prototype to eliminate that bias. To wrap up, NoctuaXR is a simple, low-cost solution to a real and overlooked problem. A $2 ambient light sensor and a lightweight GPU shader, running on the existing headset hardware, can close most of the gap between a $600 consumer headset and a $10,000 professional device. Remember the person in the dark bedroom reaching into that snack basket? With NoctuaXR, they never have to take off the headset. That's the end of the presentation. Thank you.